Okay, we've got some wave mechanics in this particular lecture, which is an extension of lecture 12, so it's indicated as 12.5. And I want to talk about something we went through rather rapidly in the last session with lecture 12, and that's the wave coordinates in space and time and per space time. In particular for the Bohr-Schrödinger dispersion, which has some interesting properties, but I also want to make it quite clear that there's something really missing from that particular very famous dispersion function that occupies almost, I would say, 95% of all quantum texts is based on that. I'd like to today introduce the use of these wave coordinates, the idea of using the zeros of waves to mark positions and symmetries in space and time. And to do that, we'll do a brief tour of this relativity scheme that's based on this, and lets you get relativistic mechanics by ruler and compass geometry. And I'll give the references and the links to those applications and the seminar and the colloquium and the various other texts that go with this idea. Then we'll return just at the end of that to the usual Bohr-Schrödinger dispersion and talk about some of the beats and time behavior that are more complicated than what we'll be doing in this first part. And I'll use the most elementary potential of almost all quantum courses, and that is the infinite square well, to show some of these bizarre behaviors, including, if we have time, the revival, well, I should say the explosions and the unexplosions that occur when wave mechanics is really doing a beautiful dance. I expect that we'll probably be talking about this in the next lecture, since some of the points are worth spending some time on. So I won't mention the rest of this content right now. Instead, let's get busy on just the basic idea of wave coordinates that are based on that identity that we talked about last time, in which you have the sum of exponentials being equal to a product, or factoring. So we need a half sum and a half difference of the exponents, the phases of the wave. But let's just suppose again, as we did last time, a per space-time, that means a frequency. In this case, I've turned frequency on the side here, so the horizontal axis is going to be our frequency axis, our per time axis, with the Greek nu. Actually, that's not Greek nu, but if I use the other one, it gets confused with V. So I'm taking this one to be a non-conventional symbol for frequency in hertz. And of course, that's the angular frequency, which is omega, that everyone uses for angular frequency. Divided by 2 pi is in hertz. And we could just as well have plotted this thing in angular frequency. The angular frequency is so many radians per second. This is just per seconds, waves per second. And angular frequency would be the number of radians of the phase per second. Well, if this is waves per second, this axis is waves per meter. That's called wave number. And it's indicated when it's angular wave number by k. But without the 2 pi, that is dividing the 2 pi out of the k, I'm going to use the letter kappa, which is Greek for k, more or less, and it stands for Kaiser. A spectroscopist who was one of the first to look at the Fraunhofer lines and the CGS unit of per centimeters. That is a perfectly good unit to use for Kaiser, certainly, is in honor of him. So, so is kappa, which is not normally used. You don't see that very much in the text, so I make a point of it. In any case, what I'd like to call this per space-time, to be more prosaic, is it's the keyboard of the gods. The idea is that I can come and push a button anywhere on this plot, here, 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 or here, say here, and I get a certain, well, number of waves per meter, but let's start with frequency. I get a certain frequency here, say 1 1/4 something, terahertz or whatever. We're not going to be specific about that, but the idea is that this is a keyboard where I can push any frequency I want. That's any key along here will give me so many waves per time, but I can also specify how long those waves will be. What's their wave length, which is the inverse of the wave number. This is the number of waves per meter or centimeter. So I call it the keyboard of the gods because usually you can't specify that. You play a musical instrument, you get a frequency, but you don't get to specify how long the waves are. That's going to be determined by the atmosphere in the room, or if it's optics, it's going to be determined on the index of refraction. So this is, you know, being a little, well, poetic or prosaic, whatever, calling this a keyboard. But that's what it is. And the idea is if I press this particular point here, which happens to be on a Bohr dispersion curve, so it would be legal by Bohr and Schrödinger for a particular mass, matter wave. If I push a button on that curve, you see, I will get some waves in space time. And here the time variable is vertical and the space variable is horizontal. That's a little bit unusual. I think most people that take calculus are used to having x be the vertical and then time be the horizontal. Almost every calculus book from time of Newton has that convention. But this is Minkowski's convention. This is Minkowski's space and time. And as I mentioned already, Minkowski was Einstein's math teacher. Called him a lazy, fat boy or dog or something like that in one of his classes. And as a result, Einstein took so much umbrage to that when later he developed the theory of relativity, which everyone thought was so miraculous and very not understandable, Minkowski wrote to Einstein and said, I've got a plot that really works well in explaining relativity. Would you be interested in this? Writing a paper about it. And Einstein didn't even reply. He was so angry about being called a something by someone who had a Polish name. This was a case of racism. It really retarded our learning of relativity because Minkowski plots didn't get used for years and years. And then not so well. So it's sort of a tragedy because as you're going to see here in our wave derivation of Minkowski's stuff, that it is very clear what's going on in the weirdness of relativity and quantum mechanics. The two are the same subject. That's why we call it relativity. But right here, what I'm showing is the space part by giving a wavelength. Now the wavelength lambda for a particular light, or whatever you want to call this, it's a Bohr Schrödinger thing, so it's not light. Light goes on straight lines, as we're going to show. But particular lambda is inverse of the KL here. So this will be 2/3, about there on this graph. And as I say, we're not being careful with units here, just playing with some numbers. And in addition to that, this dimension right here, the frequency, inverse frequency is period of time. So if I've got a 5/4 frequency, 5/4 some unit, then the inverse unit is 4/5 in time. This is a period, you see. Period between equal phases of a wave that is moving, and the rate that it moves, the velocity, is the ratio of distance to time. That is lambda to tau, you see. And let's go ahead and state all this. The velocity of waves, and if this were light waves, we were talking to Newton, we would make him very angry if we didn't say velocity of the light corpuscles, because he didn't want anything to do with waves. That was stuff that Robert Hooke did, and he hated Robert Hooke, so and some other people. So he thought of light as waves as illusions of a bunch of particles, corpuscles, going along. And his first book on optics stated this rather clearly. And so the velocity of whatever it is in a Minkowski, this is a t of x plot. The t is up and the x is horizontal, is the slope to vertical of the lambda over tau, the distance over time, delta x over delta t. So the slope here is indicating a velocity, but it's slope to vertical. This is time, you see, and if I don't move at all, my slope would be 0 relative to the vertical. That's the trouble with Minkowski plots. We're used to slope to the horizontal as indicating speed. But this makes sense, because if I go straight up here, I don't move my space dimension. Only time is changing. So I want to make sure that that's clear before we go on. So we're talking about lambda over tau, or if we're going to use those units over in the inverse space-time, it would be frequency over, that's wave per second divided by number of waves per meter. Well, per seconds over per meter is meters per second, which is what this is, and that's what we want for velocity. Okay, so given these particular values that we have here for lambda, that's 2/3, and period, that's 4/5, the speed of the wave will be 2/3 over 4/5. Or 5/4 divided by 3/2, you see. So the slope of this thing is the same as the slope here, and it is measured to vertical. Velocity of waves, or corpuscles, in a Minkowski inverse space-time, that would be kappa as a function of nu, kappa vertical, nu horizontal, is, again, slope to vertical. Now, I want to make sure that this is very unusual. Minkowski didn't, in fact, ever plot a thing like that. The conventional dispersion space is frequency versus kappa. Frequency versus kappa. And we've been looking at dispersion functions that way. This is the first time I've turned it on its side. But I turned it on its side so the velocities would match both plots. Okay, just to get you used to the notation here, which is very convoluted in a way. Okay, so this is an actual movie using Boret Web. In this particular case, it's going to be a movie about a 2-to-1 resonance. We've only got the the one part of that going here. down here is the source that has been turned on to make this wave. I call it the Bohr-Schrödinger L wave. It's on the left here. We'll have another one down the way there. It's on the right. So this will be the source L, Bohr-Schrödinger matter wave. It's a mystery source that can put out a L wave that has a frequency of 5/4 and a kappa here. That's this dimension of 3/2, you see. And the ratio of those two will make a wave that has a phase velocity of 5/6. The speed of the phase of this wave, that's what this really means, would be with a slope of 5 to 6. Okay? And we're just talking about the ratio, you see here, of this to that. I'm sorry, this to that. This over that is our speed, the lambda over tau, which is the same as nu over kappa. Okay? We're getting all this together here. All right? So that's what the wave looks like. And here is actually, you see, a whole wavelength. Now, we'll be mostly trying to draw the trace of the zeros of the wave. Most people would plot the crests, and in a couple of things that we do later, we do that. But it doesn't make much difference. It's just shifted over. But in particular, I'm ignoring, you see, the zeros that have a negative slope. I'm only picking the positive slope ones. I'm drawing a lighter line here to indicate the negative. You might call them the anti-phase or something like that, the anti-zeros. So these are zeros of the real part of a wave being plotted as it goes through time, you see, drifting off to the right. Okay, so it's a wave that comes from the left and goes to the right. All right, well that's one of the waves that we're going to have come out of a source here. There's another source, the R source, that has a point right here. So I push this keyboard on this musical light machine as I'm pressing this one, but right now I'm just showing a picture of what happens if I only press this one. This is the situation of waves. Waves that are going more rapidly than the others. The others are about here, these are about here. But in particular, these are the waves that have a frequency of 5 units, and this one a kappa waves per meter of 3. Okay? Now the frequency 5, you see, is being measured this way. That is the frequency scale, and then the kappa scale right here is this axis, and it's the one that has 3. Okay? So translating that point over here, okay, gives me for the inverse of this, the kappa inverse is lambda, the wavelength. Okay, 1 over kappa r is a third, and then a fifth is the inverse of the frequency. This is the wave period, very short period, you see, for this. Now here I am only drawing, well, you could say the crest, but I am drawing the waves that have positive slope. The zeros that have positive slope. Okay, so this is going to be a wave that has a speed of lambda over tau equal to 1/3 the lambda divided by 1/5 of the tau. Okay, or it can be frequency r 5 divided by kappa r 3. Okay, either way, we're going to get 5/3. So it's a pretty fast speed compared to the one we had last time. Okay? Now, there are the actual waves that would be in this. If, contrary to Newton, we actually have some oscillation going on here that makes the wave do its motion. And you can see this one right here has a fairly short wavelength, about 0.3, okay, units in space, where the period is even shorter here, just 0.2 units in the time. Okay? So that's one of the other one of the protagonists. We're going to put these two together, the L and the R together. We're going to add them. And of course, when you add e to the I ka plus e to the I kb, you get something that's very different from what Newton's corpuscles paths would look like. But you have to realize that Newton's corpuscles, I mean, it's a very, for us in the living in our space with throwing things around and what, a very reasonable sort of idea. And if I just drop back here just to our original corpuscle paths, what I would say was that everything that we're kind of doing here is okay for Newton as well. He would just say that these are corpuscles that are spit out at a certain time interval, okay, say 4/5. Every 4/5 of a second, it goes patooey and throws a corpuscle out at a certain speed, a speed that makes it so that it is behind the previous spitting that occurred down here. So patooey, this one comes up, and then at this time it's here, and I go patooey, and then these two go together, you see, with an interval that is the lambda, the thing we call the wavelength. So it would be the corpuscle interval, okay? And then at a time interval of 4/5 later on, and actually 4/5 is this entire time interval, this is a half period, I get another patooey. So we could even make it so that I go patooey here, and I just go patooey for a weaker one, then patooey here, and then here a weaker one, patooey, and so on. Kind of crazy because we know one of these is referring to phase as positive, and this one's a negative, and then there's a trough here, and there's a crest here in between these things. That's what waves do, but Newton wouldn't have any of that. He would just have these corpuscles making tracks in space and time if he were to plot, you say. So here's some guys that go patooey, and I'll just do a patooey for every half period. Patooey, you see, patooey, and then patooey, another one, and then patooey, a third one, and so on, filling up the space with these lines. Okay, so that's the corpuscle theory, right? So if that were the case, and I came with this one, which is really a fast spitter, and now I just didn't bother to draw the halves in here at all because it just gets really crowded. So this one is patooey, 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 and I'm letting them have a long interval. I'm really patooing these things at a high speed, much higher speed, by almost factor 2 than the other one, okay? So putting them all together, you see, on a diagram like this would be okay with Newton. And this would be what he'd get. That's all he would get. He would get an overlapping of patooey tracks in space and time. We do not get that. No matter what kind of wave we get to see the group and the phase. That's what we actually see. And they're very different wavelengths, speeds, and so forth, periods, than anything Newton would have conceived of. So this is a major break right here with the corpuscle theory, which of course has been discredited for hundreds of years, but it doesn't hurt to discredit it one more time. Robert Hooke and those guys were right. There are waves, and they're very important. If anything, it's corpuscles that are falling and particles that are things that should be under suspicion. But this is very simple arithmetic that we're doing here. Remember that when we did e to the IA plus e to the IB, I apologize for not getting that equation up here where it belongs, but e to the IA plus e to the IB is equal to a factor, e to the IA plus b over 2, half sum. And we can swing the camera around. I realized, thanks to TC, that we in fact have our formula sitting right here waiting for the geometry that follows from it. But e to the IA, and that's kx minus omega t is this phase right here, and some other kx minus some other frequency times time is this one. So these would be the two A and the B waves that we're looking at on the other screen there. And the waves that we're about to discuss is the phase part. That's e to the IA plus b over 2. And then multiplied by e to the IA minus b over 2 just gives you e to the IA. So that takes care of him. And then her right here is e to the minus IA minus b over 2, giving e to the IB. Okay? Well, this one comes out to be a cosine that envelops the phase which lives inside. And that's what you're seeing an actual example of in this picture here. You're seeing the group wave on the outside with a heartbeat of the wave inside. Okay, and so the inside wave is going to be the A plus B over 2. That means that you're going to take these two waves, left and right, and you're going to add the frequencies over 2 to get the new frequency for the phase. And then you're going to do the same thing with kappa. That has to be added and put over 2 as well. So these numbers that we're talking about here, namely nu R 5 plus nu L 5/4, okay, is one of them. That's 25/8 if you divide by 2, 25/4 to start with, okay. And then this one right here is 9/4. That's the sum of this and that divided by 2. So there is our new value of nu, 25/8. That's a result of these two, something that Newton wouldn't allow. And same thing with the kappa. We got a brand new kappa as well, 9/4. Okay? So we're going to have some kind of wave here that is 9/4 and 25/8. Well, let's check it geometrically. That's what's so beautiful about this, is that I simply take this vector here and tack it on head to tail to this vector right here to make a parallelogram, you see. There's the parallelogram that would be the sum of these two waves. Okay? Let's trace it one more time there. There's the original R vector just moved up here, being head to tail added to the L vector. It's from the head of the L to the tail of the R, and then the R extends up to the sum, just as the reverse. Now this is an abelian thing here. This adding of waves is an abelian process, and the parallelogram is meaningful. And the center of the parallelogram, right here, is halfway along the sum, and there's where the vector P for phase resides. And it is, as I said, L plus R vectors divided by 2. So here's the vector sum being carried out, giving these numbers. Okay? And from those numbers, with their inverses, I construct the space-time thing. Remember, this is inverse space-time. So what we're getting here are a new set of wavelengths and periods that are inverse to the respective kappa and tau that we're getting, well, kappa and the, I'm sorry, the inverse of the kappa is the lambda, inverse of the nu over here is the tau. So we flip that, I get 8/25 instead of 25/8, and flip the 4/9 here, I get 4/9, okay, which is very close to a half, just a little short there, and that gives us all the information that we need to make. And these are definitely not corpuscle tracks. These are tracks of what's inside that wave, and you can see them crossing right at their particular time. You see, there's that particular zero, and then there's that particular zero, and so forth. Now, that zero is due to something else, the group. Remember, these are products. This is the product of the phase part, which is a half sum in the exponent, with the group part, which I'm going to show in just a second here. Okay, so I want to make that clear. And then the ratio of these two, lambda p and tau p, the wavelength, you see, of this wave right here, which is shown. There's a typical wavelength right there. Okay, and this time you really like to put the halves in there to see where that's going to be. So, so far so good. Is this making sense?
Yeah, but the peak of the after that wavelength, the peak is a little smaller than the other peak, and it seems that the wavelength should be
this quantity here you're talking about.
He's thinking that the real parts are periodic within those envelopes.
Oh, right. This phase
out.
part here, you see, would have a constant amplitude, but it's being corralled by the group, right? And that's what makes it very confusing, because I'm not going to count that
the
as
magnitude
a zero.
will decrease.
Yeah, I'm not going to count that as a zero for the phase. That's a zero for the group. Okay? So that's what makes this really tricky. All right, when you draw it. Okay, is that so far so good? Because now we got to do the same thing for the group. Well, not quite the same thing. It's half difference. There's what the wave actually looks like. You can see all the undulations that are both of these things happening. But we'll come back to that. Now I'm doing the group part. The group is the difference, half difference, between the R and the L of this source. And I didn't put the source there, so I can't point at it. But the idea is that I need to take these two vectors R and L and subtract. Okay, here we added. Now I subtract to get the G for group. Okay, well this comes out to be 15/8 and 3/4. Now remember, this is inverse, so I got to flip these 15/8 and 3/4 into 8/15 and 4/3. Here's the 8/15 tau period right here. A little bit, a little bit larger than a half. Okay, that's 1 over the new G. Okay, the new G that I'm referring to is this right here, 1/2. Right. So I flip that to get 8/15. All right, that's the period. Okay. And then the wave number right here, the kappa, our group kappa, 3/4, flip of that is a wavelength. This is pretty big, takes up the whole picture here practically. Okay, so there's 4/3 right there for that one. Okay, so no patooey here. This is all very smooth interference of these two, making this whole picture. There's the phase that's being corralled by the group. Okay, so there's what it actually looks like. Now, at this point, it's probably a good idea to show a picture of this thing, what it looks like in motion, because that's time going along there. And so I'm going to go ahead and see if I can just click on this. This is something you can do yourself on the web, okay? And just pull up that wave, okay? Now, TC has ascribed a code to this particular setting, but of course we can play with this setting very easily. I can go here and say, I just want to look at that first one, the one with the low frequency, okay? And I click on the right, and I decide whether I want to have this be this particular one right here. And if I do, I get nothing. I've killed it. So now you see that one that had all of the lines going along. This is the R, okay? Now I'll go back. Another thing you can do is you can put the other one back. And you can make the phase anything you want, you see. You just set it, and the amplitude too, but let's just try to keep the amplitudes equal here for the time being. Really wild stuff happens when you don't do that. We'll talk about that later on. So here we are back as soon as the thing goes through a full cycle. It's totally periodic and will reproduce. And there you see the group showing its placement, and that's something else that we can do with this. Click on the right and look at your group zeros and your phase zeros. And I don't know whether this is switched around quite yet.
It should be. If it's not, we just flush the cache.
Yeah. That one should give you little lines going along on the group. So that was the group zeros pointed out by an arrow. You can see it right there. Okay?
You can turn your frame rate down a little bit so that you can scan.
That's right. You can go up here and just go there, click on it. Won't hurt to slow it down because it's moving pretty fast. Okay, so there's your group zeros, and then the phase zeros right here are being shown as well, and I'll just return that. So you see the phase zeros making the fine lines that we had colored in blue when we were showing the phase. And this is the overall phase of these two waves, okay? And then the group part, the green part, is making this. And that's what's really screwy about this. This is a Bohr-Schrödinger wave, and you can see the group phase is really fast compared to the that of the actual phase, the stuff that's inside. That's wrong. Having phase velocity greater than group velocity is a bizarre situation for most of nature. We're going to fix that today. That's called relativity. Relativity, really. Okay, so there's the plot. A small section of it. We're only getting half a wavelength in here, and that's something we should fix so that we could do a double scale like is in the pictures I was making my graphs on before. Okay, I'm going to return.
Sorry, does this have a group velocity bigger than phase velocity?
Yes.
Yeah.
The group is outrunning the phase. That's not supposed to happen. And that's why they don't mention it in quantum mechanics. It's an embarrassment. This is a terrible embarrassment for Bohr and Schrödinger. We'll fix it. We'll see what's wrong. But yeah, if you ignore relativity, that's what you get. Okay, it's still okay. I mean, you can do a lot of stuff with this wrongness, but there's some very important things that you will not get right. Okay, so if I can go back to the original, I will escape. I will just simply go and get back into my lecture day. Okay, so we were just looking at about this much going by, right? Now here's a bigger picture of it. Okay. Now let's take a look at what it is we have if we put both the phase. Now there's the phase lines right there, see, going through the zeros of the phase wave that are not caused by the group. The group line is going through there, making them both zero, right? And same place there, you see there's another group line going through there, making that zero all the time as it moves along. But the phase part, you see, those are the first lines we drew that are due to this vector, you see, are not as fast as the ones for this vector right here. You see, this one is a bigger slope relative to vertical, so it's the fasty. This is the slow one, you see, right there. And then slower than that is the L, you see, and a bit faster than the group is the R behind there. Okay. I'm sorry. The R behind there is not as fast as the group. The group is a little bit faster than the R. It's behind all of this, along with the L. Okay, these two components. All right, but you can see a parallelogram made out of the G and the P. And it brackets very nicely a trough. These are troughs of the wave. You see the dark region means down, okay, and the high region means light. Lots of light here, very dark there. In the trough, negative, I should say. Okay? There's a more definite picture of what it is we were looking at there. Okay? Is this making some sense? All right? There's when you put all of it on top of it, including the particle, the red, and the purple. Okay? Those are the corpuscles that Newton would have. Look how much more smooth all of this is if we do the wave interference. Okay? And make a coordinate system. This is the technique that works for any wave that you can possibly imagine. And of course, I'm talking one-dimension space and one-dimension time. But it's a really simple way to think about how they interfere with each other. And you get a coordinate system in it. There's everything emphasized at once. Quite complicated. If I show you this first, I don't want to see wave mechanics again, right? But we build it up geometrically, and it does make sense. Now, what I want you to do is use this to make Einstein-Lorentz-Minkowski space-time coordinates. Okay? The light waves are very well behaved for doing this in a way that is far beyond anything that most people imagine. I showed this picture before. This is something that comes out of Unit 8 of the Classical Mechanics with a Bang. And it's a whole, it's an older but quite different description than what we have now. But the basic ideas are all pretty much the same. It's just a better, the new stuff I think is a better description. Plus I'm using modern graphics now. This is our old graphics of the situation with the pulses. And this is what we're going to talk about right here. We'll get to the pulses a little bit later on, but mostly in the next lecture. But, and this is where Newton gets a little bit of, shall we say, a victory. Because when you add up harmonics, you get something that looks like a bunch of corpuscles going along. Okay, so let's see what it is we have. What we're going to start with is just two lasers, one of them pointing this way that we talked about very quickly last lecture, and another laser that's got a frequency and a K, or a nu and a kappa, that puts it pointing at always 45 degrees. If I put a little C onto the K or kappa, that's the miraculous constant speed of light, which, say a few words about that as we go along here. But if you just have a laser instead of pulses, then you get a coordinate system that is really nice. It's a Cartesian coordinate system. The one that I just showed you is anything but Cartesian. This one is Cartesian. If they're both the same frequency, and if they are the same frequency, they have to be the same wave vector or length. That is what you get. Now, we should get a picture of that. And the idea is that what we're going to do is we're going to, I'm just looking at the top set of figures here, I'm going to come this way, or have this thing come at me from the left, and Doppler shift this 600 terahertz. Now we're going to be specific about green frequencies and wavelengths. We're going to have a half micron wavelength of this light be raised by a factor of 2, a full octave, to from 600 terahertz to 1200 terahertz. That's going to take it completely out of the visible and put it in the ultraviolet. So we're going to have a very blue, a 1200 terahertz coherent light beating us from this direction. That's that thing. And in the process of doing that, if I change my speed this way, or this thing this way, enough to do that, then the laser on the other side, the one that's coming this way that I'm running away from as I collide with this one, as I'm running away from the left laser, that's this guy right here, I'm going to Doppler shift it by the same factor down, so 1/2. That's a time reversal idea there. I could spend more time on that, but I won't do that right now. This is something that's taken for granted, so I won't belabor it. But you should belabor it. It's a very important time reversal axiom. I need 2 axioms here, and that is that the speed of the waves can Doppler shift but not change their slope. And the other one is that if you're going the other way, it's inverse. Okay, so that's what I want to look at closely. This is really not close enough, but I think you can see the phase wave in there going through a very strange dance. And it's the one that's making what used to be infinitely fast zeros are now slowed down, and the ones that were absolutely no speed at all have speeded up. You see the group things there. That's what we want to look at closely and do a little bit of animation to see that. So this is just from last time, but it is worth mentioning. Now, when we're done here, we're going to have a new kind of coordinates, which is Minkowski's. The new time axis is going to have some dilation. It's going to be going at the speed of whatever the object is, that relative speed between observer and laser system. And the other thing that's going to happen is what we call the boundary between future and past. That is the x-axis, now an x-prime axis, or the original x-axis if I'm the prime coordinate system, which in this case the moving atom is. That's going to tip, and that means that a part of it is going to be revealing over here the future of the object, and over here looking back into the past of the laboratory. So there's all that weirdness of relativistic time and space that is being exhibited by what waves do. They interfere with each other, and that's all there is to it. So we need to discuss this in some detail. Now this is what's in the current article that is at this point in draft form without very many references, but nearly, I would say, complete of what we're going to submit. The relativity in quantum theory by ruler and compass is clickable by that object right there. Should bring it right up in a PDF form, and you can save that. Here is the picture of the per space-time, that's the frequency, and the wave vector, omega and ck are the two coordinates here. It could also be nu and c kappa, but we are using both the omega value in some units and the hertz value. So there would be a new scale right there. And there's 600 terahertz right there, you see. So these two vectors, when they are summed, we'll give you a point up here, but summed over 2, they give me the group vector in space-time. Now remember, this is not been turned over. I haven't turned this thing sideways like I did in the example we just went through. So therefore, there will be a flip. The g here, which is this vector minus that vector over 2, is horizontal, whereas the sum of them over 2 is vertical. It's just the opposite over here. This right here is the image of this vector in the mapping 1 over. And so over here we have these tracks that have 0 slope relative to the horizon, but infinite slope relative to the vertical. And remember, that's the way we determine speed. What's cool about doing the old-fashioned dispersion plot is that the slopes over there relative to horizontal are indication of velocity. In this case, an infinite slope means that the zeros that make this line go infinitely fast. And that's a property of phase. Phase should be really fast, not less than the group. Here the group is 0, you see. It's got 0 slope relative to the vertical, which is what it is in a Minkowski plot. But over here the g is showing 0 slope. That indicates that it is making something that doesn't move over here. Just to bring that up, because everything we're going to be showing in a dispersion plot, I'm not going to do a Minkowski dispersion plot. He didn't either. So there's some niceties to doing it, because then the velocities here match the velocities over here. You could make a Newtonian plot here and then use this one, and they would match each other. Okay? We're going to be fighting with Newton for the rest of our careers here, aren't we? But let's go ahead and we'll be showing this again and again. This figure, again from this thing, this is, the last one was figure 4, this is figure 5, is where we have a situation where we're moving fast enough between, relative to the lasers, or the lasers are moving relative to us, that it looks like a 1200 terahertz laser and a 300 terahertz laser instead of two 500 terahertz lasers. So here's the blue one, ultra blue, ultraviolet, quarter micron light coming, very bad for any part of your body. And then this is just a gentle infrared, 1 micron, my gosh, warm light that you can't see, okay? And they're going to run into each other and make this. That's what we wanted to study. But the control panel for this, namely the Fourier space for this, started out with a baseball diamond that had an equal first base and an equal third base line, and became a baseball diamond that is very warped, with a very long first base line, double what it was, and a very short, half of what it was over here, 300 terahertz and versus 1200 terahertz, whereas before it was 600 versus 600. So we get a new group vector that comes rising up above the thing, where it had 0 speed before, it now has some speed. Okay, that's the group. And then the phase, okay, this thing right here, which used to be over here vertical, that means infinite slope, corresponding to infinite speed over here, it has slowed down, but it's still faster than the speed of light, which is a 45-degree slope of 1. Okay, the two of these are on equal side of it, so it's very simple arithmetic compared to what we just did. And that will correspond to, and here will be the actual velocity line right there, the time axis, the new time axis in space-time. It used to be vertical. Now it's not anymore. That's very weird. What's even weirder is that the space axis has risen up. And there it is, you see. It used to be horizontal, corresponding to light with zeros going infinitely fast. It is now slowed down a little bit. And this one right here, which used to be absolutely no speed at all, has speeded up to exactly the velocity of the laboratory relative to the observer here. So this is the real relativity at work here. Now, what we want to do is show some of this in animations. And so I'm going to pick on Relativity app, and I don't have this one set with a nice thing to where I want it to go, so I'll have to mess around, but that won't hurt. You'll at least see how to explore this thing on your own. So I'll click on this right now and come up with what this whole relativity thing starts with. Basically, if you really learn what a sine, a tangent, and a secant are, you've got relativistic wave mechanics completely described. That's a little bit of an overstatement, but it is not as much as you might think. Anyway, I'm going to go right to the per space per time. And that's this, which is going to start out with them equal. Okay, so this is what's going to happen to the wave vectors associated with the right moving laser and the left moving laser. Okay, and you just grab these little bullseyes and you move things to see where they're going to go. Now, what you can do is you can go up here to this button right here, and you can get to see the group and the phase vectors. And while you're at it, you can also ask to see the Minkowski grid. And it isn't showing up terribly well with that. And I'm going to go ahead and turn off some of the stuff that's here. When you click on the right, you get a thing that lets you turn off a few things. So I go ahead and keep the B circle, but right now I don't need the P or the G as phase and group circle. I don't really need the red shift, which is not showing at all now because it's not shifting. Mm-hmm. But I think that is all I'm going to need. I'll do a Minkowski with only one grid, since they aren't showing all that well anyway. Okay, and return. Okay, so as I shift these two, that means as I move it over here from, I was trying to balance it right where they're both green, but that doesn't seem to be working right at the moment. I'm going to get this one bluer and bluer, and the other one redder and redder, okay, until we have about the situation that we're talking about, which is this one half as big and that one twice as big. That would be a laser frequency here. See if I can get B equal to 2, which is just about right there. If I can get just a little bit more on that thing, what's going on? I've got to go down this way. There we go. Close enough for government work. Okay, so that's the situation that we have. And I don't know if you can see the Minkowski graph with its bent things in there. I can hardly see it myself, so that's not going to show up on the video at all. It might be that we could change the contrast and things like that a little bit. I'm going to go whip over to this graph over here to let that see. This is the actual plot that we were looking at a little bit yesterday, but I'm going to go ahead and run it right now. But there is in space-time, you see, there in space-time is the entire grid. So it's analyzing that thing that I want to do. And you can see the phase part of the wave cutting its way along, and I'll use my own fingers to point this out, starting right there and then coming back right here. I'm going to wait till it comes around again here and show you. It's really fast. It wouldn't hurt to go ahead and slow it down even more so that you can really look at where it's going. You see, this is a phase 0 that is making our new space axis. If in fact, this was the origin right here. This is more like the origin right here. So there's the one making the space axis, whereas the group is making the time axis. Okay? As our other group of zeros making the other grids that go parallel to the new time axis. And the new coordinate axis, x-axis here, has this one has been made by that phase right there. This one's just passing a node and continuing along this grid line of constant time. That's the thing that separates future and past for that particular instant. And it's operating everywhere. This one is a little persistent. You see, it's a group holding this thing. This phase is not 0. Here comes the 0 phase to meet the 0 group, and that's an intersection of a time grid line and a space grid line right there. And then they go on their separate ways. The group continuing up this way with a slope of 3/5 in this case. We'll calculate all that stuff. And this one traveling at a 5/3 of the speed of light to make the separation, the now lane you might call it, between past and future.
Isn't that the phase velocity, or
the phase velocity
is
this, and it is a lot faster than the group velocity. Remember, it's just sloped vertical. This used to be 0, now it's this, which is 3/5.
What are these waves? There are 3 waves. One of them red, blue, and
Amplitude.
the dark blue is what we colored our phase, the P.
phase.
Okay, and at this point I might go ahead and get back to the lecture so I can point at all that
Blue
stuff.
is real. Cyan, the sky color, is an imaginary component. And then the green is the...
This is a much better diagram here. The idea was we started out with our right-hand laser here and our left-hand laser right here. I shrunk the left-hand laser down to L prime, okay, at the same ratio that I expanded the right laser up to here, okay. So those are the components that we will not see because interference will only give us this. It'll give us the half sum which is the new P. That's the old P right there. And the half difference between these two, that's this minus this over 2. That's this vector right here. So there's your group vector right there. That's the thing that's determining the outside envelope. That's the one that over in space-time will be going at the actual speed, relative speed of observer and laser lab. This one right here, you see, in this plot, the way we've done it here, frequency versus kappa, this corresponds to infinite speed over there. This corresponds to 0 speed over there. This has come up from 0 to that, and that's the speed of the green envelope, which you're seeing on the movie there, moving along at a relatively sedate speed of 3/5 the speed of light. The one that's following these lines here and here. And then inside that envelope is something going a bit faster. So now it's doing what it should do. The phase, the blue stuff, this stuff, the phase is going faster than light. In fact, it's going 5/3 faster than light. So that is the real part. See the imaginary part there, just for curiosity. It is also going at that speed. But this is the one we're letting to draw the coordinates. The real part of the wave is drawing the coordinates everywhere. This particular one is the responsibility of the phase. Now it's meeting one that's the responsibility of the group. The group, of course, is the green thing. It's making this line, and this phase will continue out the other side and make that line. So it's really quite a dance. Quite an incredible dance. This is about as simple as wave mechanics gets. But it's all we need to derive the rules of the universe. Up to a point. I'm being a little bit prosaic, over poetic is probably a better word for it, of what this does for you. You have a complete map of space and time. In any number of dimensions, but it's really hard to do more than one or two dimensions of space and visualize it. So we're sticking with one dimension of space and one dimension of time for the moment. Okay? Is that making some sense? All right. So this is the graph we need to analyze. I want to make a table of everything that's going on in that graph using our groups and phase. Okay, that's the thing. But to do that, we have to realize that the driver for this, the first order effect, the thing that should be first in every relativity and quantum mechanics book, is Doppler shift. It is first order. It's very simple. You go toward a wave, you hit more waves, so the blue shifts up. You run away from a wave, you get to see less, so the frequency that you see downshifts, red shifts. Okay? So the red and the blue are the prime movers of relativity and quantum mechanics. And right now, we're going at just the speed that one of these is 1/2 and the other one is 2. They're inverse of each other. And we're going to use a parameter that is the logarithm of that shift. So we're going to write the actual Doppler shift, either red or blue, as an exponential. And they'll be inverse of each other. So the red one will be e to the minus something. That's something, we use the Greek letter rapidity for red shift, I guess. But in this case, a red shift. But Greek R for rapidity. That is an actual name that you'll find in a few of our more advanced relativity books, mostly for general relativity. But it should be at the beginning of every text in physics. And here is e to the plus rho. So it's a combination of those two, namely half differences and half sums, that is going to fill this table with parameters that completely describe the relativity and mechanics that goes on in this little space-time diagram. So let's get started with that. In particular, I'm going to start with, since we have a ultraviolet 2, that's the value of this guy right here, 2 over 1, and then an infrared 1/2, that's this guy right here, and it's the half sum of those that we're interested in. That is the hyperbolic cosine of that variable rho. And in this case, it's 5/4. What that means, we'll see here. 5/4 is 1.25. We're going to see some things here that are 1.25, namely the elevation of this vector right there. That's what it is. It's half sum of these two vertical dimensions here. There's the Doppler shift blue, e to the minus plus rho. There's the Doppler shift red, e to the minus rho. 1/2 and 2 being summed. Okay, 1/2 plus 2. Okay, talking about 5/2 divided by 2 is 5/4. Okay, that is the hyperbolic cosine of whatever it is the logarithm of the Doppler shift at that particular setting. This whole setting here is going to, this whole table is just devoted to that particular value, these particular values, 2.5 of the Doppler shift. So there's the hyperbolic cosine, 5/4, 1.25 right there. It's also going to be over there, but this is the one where it shows up first. Okay, so far so good? Well, there's also hyperbolic sine. It's 2 minus 1/2. Okay, that's 3/2 divided by 2. 3/4. Okay, 3/4. 4/5. 4/5. I'm sorry, 3/4. 3/4. What am I talking about? I should know that much arithmetic, shouldn't I? Okay? So, one of these is the phase frequency, the other is the phase wave number. Here's the wave number axis. There's the frequency, waves per second, waves per micron, I guess is what that is. Here it's waves per 300 terahertz. 300 terahertz the unit here. Actually, it's 600 terahertz, so that's actually 1 in those units. But these are the new values for what used to be 1. 1 has grown to 1.25, and 0 has grown to 0.75. This thing used to be right there. That vector B used to be right there. And the new group vector was going to show up in a minute. You can see it hiding down there. It used to be right here, and it's grown to there. We'll get to that in a minute. Okay. And here are two important variables for our analysis in per space-time. Okay. Well, they're going to show up over there in inverse form, just like we were doing before.
Are you looking at waves while we have velocity?
Say that again.
I mean, are we looking at waves when we have velocity?
Yes. Yes.
We
were looking at two 600 terahertz lasers. One on one side and one on the other.
Yeah.
Okay. And one of them is coming at us. The other one is running away.
Running away.
Or the same thing. They're sitting still and we're moving. The only thing that counts is relative motion here.
Yeah.
And that's true of all light.
are those relation for K phase? No, K phase.
Phase.
Yes, I don't know where they come from. I mean,
Well, they're coming off this graph. And we're talking about the phase, so it's this vector. And this is the frequency axis right here, okay? And this particular, that's this guy right here. But the other coordinate is this axis. That's the wave vector. That's the C kappa. Whereas this right here is the nu. Now we put the C on there so that this will be slope 1.
is there velocity in rho?
Well, rho is very close for low speeds to the relative velocity divided by c. It's a dimensionless parameter. Okay? So
Velocity divided by c.
yeah, the normal, what they call the relativity parameter, is u over c, or v over c. Okay? Rho starts out very close to that. But after that, u over c is useless. Rho remains beautiful. Rho is so beautiful that it brings Galileo back to us. You add the rhos to get a relativistic group transformation. It is a Galilean addition that is perfect when you use rho. And only approximate, you see, is it equal to u over c, which Galileo thought u over c was the thing that you did Galilean transformation to it. This, I call it Galileo's revenge, that this rho does what he wanted it to. Okay? So do a lot of other things here. We'll get to that later on. So,
another one will
we're
become
talking
more
about
and more clear
sizables.
as we fill in the table and move back.
You can see what we're talking about here. If you take the ratio of this to this is 3/4, this is 5/4, right? That's the slope of this line to the vertical, 3/5. And this one is, this group thing we're going to talk about in a minute is over here, is that's the one that actually represents the speed. Starts 0 here and comes up to 3/5. This one is really 5/3 in this graph. Okay, so it represents this really fast stuff over here. Okay, let's go ahead here. Here they are both together, 3/4 and 5/4. This is the p prime vector with those components, sine and cos, hyperbolic. Okay? And while we're at it, if I know the frequency of the phase, I can get the period of the phase by simply inverting this as a coefficient. Okay? 5/4 becomes 4/5. So here's the period right here, and those are phase lines, and there's their intercept. That is my period right there. Tau of the phase. Sec hyperbolic, the inverse of this. So these are the first two main entities in this table, the tau phase and the nu phase. Frequency of the phase part and tau of the phase part. And by phase part, I mean the heartbeat of this wave, of this thing that's going to be, that becomes a matter wave. We're making a matter wave here. It obeys all of the rules of mechanics precisely. And that's the guts of it. That's the heart, soul of it, if you're religious. Okay. So, these two numbers are very important. Okay. Now, I should point out that the slope of this is the ratio of the 4/3 and the 4/5. That's 5/3. Always faster than light. While this is the p-slope right here, 5/3, another way to look at it, okay? That's the phase velocity, right there. Hyperbolic cotangent. Hyperbolic cotangent of that rapidity is this one right here. And while we're at it, the cosecant is in there too. Not doing much for us right here, but if you want to look at the lambda of the phase, there it is, right there. This is the period that those intercepts on this axis. That's the lambda of the phase. And remember, we're tracking all the zeros here. So we got to go 2 zeros to make a full wavelength, 2 of the phase zeros to make a full wavelength. Okay. So I'm drawing this guy with positive slope. I'm not going to look at the negative slope as a measure of wavelength. It's in between those two. Okay? Here's group. We're skipping a lot of slides in this lecture, by the way. We take these individually, one at a time, in the actual talk here. But this is the group right here. Okay? It has a frequency of the group as well as a kappa of the group. Same numbers. They're just flipped. It's, instead of being sine and cosine, it's the reverse. It's symmetrically deployed on the 45 degree. So that one is 3/5 instead of 5/3. Always slower than light. By just as much as the phase is faster than light. Always that way. And that pretty much fills the table. The only thing that's missing here, I guess, is for some reason the phase velocity was left out of this final thing. But I want to point out, there's the full table right there. I want to point out what the old-fashioned notation is. Okay? If the group velocity, that's this, there's your usual relativity parameter right there. That turns out to be the hyperbolic tangent. That's what they call beta in the old-fashioned notation. Or V over C, U over C, V over C. Okay? So there's the old-fashioned relativity parameter. There, right there, is one that's pretty important for us. 1 over 1 minus V squared over C squared, the 5/4. Okay? It plays a lot of different roles, but one of them is our frequency of phase. Okay? But the real name for it is Einstein time dilation. There it is, shown in space-time. Okay? The new prime phase is 1 1/4, 5/4. This used to be, this would come down here and be 1. Now it's up to 1.25. That's a second order effect. This right here is flat. This is first order right here. But this other one, the inverse of it, that's this right here. That's the track lambda prime of group. Lambda group. Seek. That's called Lorentz length contraction. Here it's contracted by 20%, while the dilation is by 25%. They're inverses of each other. Everything in this table on one side is the inverse of its corresponding thing on the other side. So this is summarizing what you get by doing phase and group, half sum, half difference. This shows the parameters that you need to work with in any theory of mechanics or relativity. Now I want to show that. This is sort of going a little fast, but there are things that come up here. First of all, because that new baseball diamond had to have the same area as the original baseball diamond, the new phase vector, you see, has to lie on a hyperbola. Should this be a surprise after what we've done already when we discovered that this is the hyperbolic cosine and this is the hyperbolic sine? They're called hyperbolic and cosine and sine because if I look at it this way, this is a cosine and that's a sine of a hyperbola. So one of the things we do is we do an amazing marriage of the hyperbolic functions with the circular ones. That is so cool, and I haven't seen it anywhere, but it makes a diagram that I would use if I had a kid growing up. He was 3, 4, 5, 6, or just learning a little bit of geometry. I would take a diagram that shows all of those on a circle and a hyperbola. And of course, TC has made it animatable so you can watch them move, and we'll do a little bit of that right here. But all of those functions that you learn in the school are part of our quantum field theory, relativistic quantum field theory. Those are the parameters we should be using. And you sometimes use the circular and sometimes you use the interchangeable. They're completely interchangeable. Now most people make a fuss about how the cosine of x is equal to the sine of ix and vice versa. And then they don't go anywhere with that. And that sort of is just an obvious truth of mathematics. But the thing that we're discovering is much more subtle than that. The sigma, turns out, is stellar aberration angle that goes with this. Now this takes several slides. We start with this. And basically, we're getting here in a few steps both the Einstein expression for energy and Planck's expression for energy. But he didn't use rapidities or anything fancy like that. That's what we're getting right here. So the famous MC squared shows up right as we take this apart. So these functions, this function right here, the cosh of rho, that's the Hamiltonian. This is the Lagrangian. They are inverse of each other. That's just really surprising. The Hamiltonian, a function of momentum. There it is. We get that in the second step once you're doing that. So these two right here, cosh and sinh, are energy, frequency. That's what Planck and relativity come together. Okay? And then this is what they're functions of. They're functions of this thing, which is the kappa. The phase is the thing. This is the guts of the wave, telling us what it means to have energy and to have momentum. This is the de Broglie thing. Okay, 16 years later than this, and this is 5 years later than that, sort of rediscovering that. And all it is, we attach a scale effect. We just getting the right units for our phase to match it to something that looks like Newton's kinetic and momentum. So this is a lot of stuff, but it's part of everything we do. So it really needs to be digested. Now, if you go in and look closely at this hyperbola, it's a parabola. There's Bohr-Schrödinger. And what they threw away was MC squared. They threw that away from the phase, put it back, and then the phase speeds up and passes the group. Group doesn't change. Group doesn't care about origins. You can put your origin here, or you can put it way down there, mc squared, just down here, and it won't change your physics much. Because you're only measuring differences in frequency or energy. The absolute value is not something we're detecting. That's the heartbeat we can't see in the wave. That's the phase. But it's going by this origin that fast. That's huge for something that weighs anything. For 600 terahertz, it's only 600 terahertz, you see. It's only this height right here, which is 600 terahertz by our development, okay? Well, we're talking about a really tiny mass here, a really tiny rest mass, by just sticking 600 terahertz of light into a thing. However many photons you have, those are all hyperbolas that are parallel to this one. That's probably on the 100,000th hyperbola. And the other thing that's really beautiful about this, and this is part of the colloquium you can click on, although it will take you to the front page, the way I've got it set. We'll obviously figure out ways to get to certain pages of that later on. But the geometry of this is so beautiful that I just need to play it a little bit for you. And I will do that, if I can, right now by clicking on this. And of course it brings me to the front page, so I have to whip over from this, where we're putting the sines and tangents together, to physical terms. And there it is. There's the hyperbola, that is the Hamiltonian, the hyperbolic cosine, and there's the momentum, is the hyperbolic sine. So those are the very nice coordinates, aren't they? But let's go ahead a little bit and look at another possibility. There's an angle called the stellar aberration angle, and it is the polar angle of the Lagrangian, and the Lagrangian is a function of group velocity. That's what comes out of this. Really beautiful. But they all work together, you see. They all work together. You can grab any one of these bullseyes, the Lagrangian bullseye or the Hamiltonian one. And you can see how all these things vary as you go to higher and higher speeds. And of course the group velocity is limited by c. The Lagrangian is keeping track of the total phase of the object. This one runs free, go as large as you want. There's no limit to it. But these and the stellar aberration angle are limited. And you can go ahead and just make a real mess of this thing by showing everything. There's all of the functions that are at work here. And I won't bother. I guess the Minkowski graph is on. It's just not showing up very well there. I shouldn't have touched that. That's the way you make adjustments on this thing. Okay? So you'll see that the sine of the stellar aberration angle is equal to the hyperbolic tangent of the rapidity. But that then means that the hyperbolic sine of the rapidity is a tangent of the stellar. So you have this flip between sine and tangent. And that was manifest in that table. And then the next one that probably look at is the cosine here of the stellar. The cosine of the stellar 6988 is equal to the sec hyperbolic of rho. Well, that means that the sec of sigma is equal to the cosh of the rapidity. So the sec and the cosh play with each other. In the cosec, right here, 977, it's playing with the cotangent of the sigma. So they're married, they're cousins. We call them city cousin and country cousin. This is the city cousin. They never get outside of a circle in town there. There's the there's the cotangent, and the cosecant is country cousin. That goes very big. It's out in the country, so to speak. So this is just to give you a feeling for the geometry. Now, tangents are incredible. This is a Legendre transformation. You see, this tangent comes down, and its intercept is exactly the Lagrangian. Then the Lagrangian's tangent intercepts right here at the Hamiltonian. That's the Legendre transformation. The reason for that is that the Legendre transformation is just respecting the phase kx minus omega t. That's what it's doing. Okay, well, I think we're just about here at the end of this, and I am going to go ahead and go back to the lecture just to make sure that you see one other thing. Hamilton's first equation is giving the slope of that. Lagrange's first equation is giving the slope of the Lagrangian. Now, with the accelerating thing, you need to get the second equations. We haven't done that yet, but there's lots more to do. So we'll be taking something very simple on. This is back to Bohr-Schrödinger, but remember what's behind Bohr-Schrödinger. A huge MC squared. Okay, I'll call it that.